Hi, my name is Hermano, and this is my Physics 2211 Lab 3 video report on black holes and orbits. And this is a quick overview where I go through the introduction, fundamental principles, code, results, errors, and then talk about the discussion. And this lab had two parts. In part one, I analyzed the motion of a star to determine the mass of the black hole. And in part two, I determined initial velocity for a spaceship so it could move in an orbit influenced by both the moon and the planet without crashing into either object. My main results were a black hole mass of 1.54 times 10 to the 34th kilograms, and a successful initial spaceship velocity of negative 150 meters per second in the x direction and negative 600 meters per second in the y direction. And for the systems and surroundings, in part one, the system was the star and the black hole, and the surroundings was everything else. And in part two, the system was a planet, moon, and spaceship, and again, the surroundings were everything else. And the main physics principles used in this lab were Newton's second law and universal law of gravitation. Newton's second law says that the net force equals the rate of change of momentum over time. And in this lab, that was especially important in part one because I used the change in momentum of the star to find the net force acting on it. And I also separated the net force into parallel and perpendicular components. The parallel component changes the magnitude of the momentum, which means it changes speed, while the perpendicular component changes direction. And the other major principle was gravity. The gravitational force between the two masses is proportional to the product of the masses and inversely proportional to the square of the distance between them. And in part one, I rearranged the relationship to solve for the mass of the black hole. And in part two, I used the gravitational forces from both the planet and the moon to determine the spaceship's motion. And so for part one's code, I used GlowScript to model the star's orbit, and I set the initial conditions, including the gravitational constant, the star's mass, and the timestamp of 1 day. And then I calculated the star's x and y velocity components from the position data. And then after that, I found the initial and final momentum vectors, used those to calculate the change in momentum, and divided by delta t to get dp over dt. And since Newton's second law tells us that the net force equals the rate of change of momentum, I set F net equal to dp over dt. Then I found the parallel and perpendicular components and used the net force and distance from the origin to calculate the black hole mass at each step. And then this is the results. And you can see the star is orbiting around the black hole, and the force changes as the star moves. And since the orbit is not perfectly circular, the force is not constant. And when the star gets closer to the black hole, the gravitational force gets larger because the distance decreases. That causes the calculated mass values to vary slightly from point to point. So instead of using just one value, I took the average, and my average black hole mass was 1.4 times 10 to the 34th kilogram, with a minimum of 1.5 times 10 to the 34th and a maximum of 1.58 times 10 to the 34th. And I set a standard deviation about 1.3 times 10 to the 32nd. And for part two, I used the GlowScript model again, and I started by giving masses of the planet, moon, and spaceship, and used a timestamp of 90 seconds. The moon's initial orbit speed was calculated from the gravitational relationship of the planet, and then I chose the spaceship's initial velocity through trial and error. My final success choice was negative 150 and negative 600 meters per second. And in the main part two code, I calculated all the gravitational force pairs needed for the moon and the spaceship. For the moon, I found the force of the planet and then the force from the spaceship, then added them to get the net force of the moon. For the spaceship, I found the force from the planet and the force of the moon, then added them to get the net force of the ship. After that, I updated the velocity using Newton's second law, and then updated position using the velocity formula. I also included brake conditions, so the simulation would stop at the ship crashing the moon or the planet. And in part two, the results video, the cyan path represents the moon, the magenta path represents the spaceship. The goal was not to find one perfect answer, but to find an initial velocity that allowed the spaceship and the moon to move under the influence of both the moon and the planet without crashing. And my chosen velocity was successful because the spaceship's path clearly shows that both bodies are affecting its motions. And some possible sources of error in this lab come from the fact that the simulation uses numerical integration. So a small approximation errors accumulate over time. Another source of error is model assumptions because the simulation ignores any forces or objects outside the model system. And in part two, I use trial and error, so the velocity I found is not necessarily unique. Other valid initial velocities could also work. And finally, for the further questions for what does it mean in part one, mathematically, the net force and the rate of change of momentum are the same since F net equals dp over dt. The difference is in interpretation. The rate of change of momentum can be found directly from motion data, while the net force represents the combined effort of all forces acting on the object. Also, the parallel component changes speed, while the perpendicular component changes direction. And for what if in part two, if I wanted to model the entire system, including the black hole, star, planet, and moon, I would need to include all gravitational interactions between every pair of objects. Those interactions would not only contribute equally the dominant interactions would come from the largest masses and the smallest distances because those produce the greatest gravitational forces. And overall, this lab showed how Newton's second law, momentum and gravitational, can be used in computational models to predict orbital modeling. And thank you for watching.